The first topic that we're going to cover in this class is the structure of atoms. So, first, it's important to note that everything that you can see in the room around you is made of matter. So, we want to make a difference between matter and energy, and we're going to see that difference in several places in this class. So, first, when we look at different objects in the room, we can imagine that they are all made of matter. And if we had a magnifying glass that could zoom really, really far into the structure of those objects, we would see that they're made of discrete entities that we could either call atoms or molecules. And so, for example, in the water bottle, if we zoom in really close with our molecular magnifying glass, we might see water molecules. And those water molecules are represented by one oxygen atom and two hydrogen atoms. The oxygen atom is red and the hydrogen atoms are gray. So we can see that those units there are H2O molecules. And so a molecule is one type of a particle, one type of matter, and the water in this case is existing in its liquid state. And then we use our magnifying glass to zoom in on the golf club there on the right. And the golf club is a solid, so we can see that in the solid, the atoms are closer together. There's no space in between them, whereas in the liquid on the left, there's some space in between those particles. We can also see that the golf club is made up of one type of atom. All the atoms, all those spheres are the same color. They're all black. So what that means in this case is that they're all made of the same type of atom or the same type of element. Whereas on the left, the water is made up of a red sphere and two gray spheres. And so that's indicating that those are different elements and different atoms. And so we would say that the compound, or the particle on the left, we would call a compound because it's made up of more than one particle, more than one atom, more than one type of element. And on the right, the golf club, we can say that since there's only one type of atom there, that substance is a pure element. There's only one type of element there. So these are the kind of distinctions that we're going to get into in this chapter. The difference between what different objects are made of in terms of atoms, and what types of atoms there are in those particles, and whether the particles are solid and there's no space in between them, or they're liquid and they can move around and there is space in between them. Those are the kinds of things that we need to start with. We have to have an understanding of these kinds of ideas as we move forward in this class, because ultimately we want to understand how living systems work and how biological systems work, and they're based on the same idea. And so we're going to start at this very basic kind of idea of atoms and matter versus energy. So here's another object, an aluminum can, and we can zoom in on the aluminum can and see that if we zoom in really far, we see these spheres, and those spheres are atoms, and every sphere in this case is the same color and the same size. So we would assume then that those atoms are all the same kind of atom, and so we would say that in this case that kind of atom is aluminum, because this is an aluminum can, so those are aluminum atoms, because aluminum is an element on the periodic table. So aluminum cans are actually made out of a pure element, one element, just aluminum all by itself. So this idea of atoms comes from a really long time ago. A guy in Greece, Democritus, came up with this idea. He had a thought experiment. He said, what would happen if I cut something in half, and then I cut that in half, and then I cut that in half, and then I cut that in half? And he did this thought experiment and said, if I keep cutting something smaller and smaller and smaller and smaller, can that process go on forever? Or eventually will that process stop and I'll reach a thing that is the smallest thing that there can be? And Democritus, he concluded that he would reach a smallest thing. That process cannot go on forever. You can't keep making something smaller and smaller to infinity. At some point you're going to reach the smallest thing. And the smallest thing is called, Democritus called it atomos. So he called it an atom, atoms. And so this word atom, this idea that the smallest piece of a thing is called an atom, that came from ancient Greece, if you can believe that. Before we knew much about anything, people just by thinking about it had concluded that there is a smallest thing, and we'll call it an atom. And Democritus said the only things that exist are atoms and space. And to a large degree, that's a pretty accurate representation of the universe. Pretty incredible that somebody came up with that before we had light bulbs. Anyhow, so when we zoom in on this aluminum can and we see these atoms, what we're saying is if we cut this aluminum can into teeny, 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 tiny pieces over and over and over again, eventually we would reach a piece that is so small that we can't cut it apart anymore. And that is the aluminum atom. That's the smallest part of an aluminum can. Here's a bottle of isopropyl alcohol. And so a liquid is different than a solid. An aluminum can, all those atoms are the same. They're all aluminum. And they're all really, really close together. And that's what makes something solid. You can't really squeeze a solid. You can't compress it very much. There's no room because the atoms are really close together. If we look at a liquid, the particles are further apart. You can see space in between those particles here. And so that's indicating that these liquids, the particles can move around a little bit. They can become more dense. They can get closer together than they currently are. And so that's one difference between a liquid and a solid. And we can also see here that in isopropyl alcohol, it's not just one kind of atom. There's a red one, a gray one, and a black one. So there's at least 3 different types of atoms in a molecule of isopropyl alcohol. And so that's different than an aluminum can, because an aluminum can just has one type of atom. But this has 3 types of atom. So a type of atom is really just an element. When we say the elements on the periodic table, and you've got that table and it lists all the different letters, and those are all the different elements, an element is just a different type of atom. So here we have 3 types of atom, red, silver, and black. Those are different elements. The red one is oxygen, the gray one is hydrogen, and the black one is carbon. So we have 3 elements that make up a molecule of isopropyl alcohol. And so that's we're going to distinguish this compound, this molecule, from a pure substance like an element that only has one element. This has 3 elements. So that's different. This is a type of particle that we would call a compound, whereas an aluminum can we would call a pure element because it's one element all by itself. So how do we know that this is true? How do we know that Democritus was right? Well, we've done lots and lots of experiments for a long time, but at this point, we actually have technology where we can zoom in so close that we really do have a magnifying glass that can see atoms. It's called a scanning tunneling microscope. And there are other instruments that we can use to see atoms as well. And so you can see that what this instrument produces is an image that looks kind of like mountains. You get these green mountains, right? Well, those mountains represent atoms. And if you look closely at each individual peak on the mountain, you can see that it kind of comes to a peak and then it goes and it turns a little blue, and then it comes to a peak and then it turns a little blue and comes to a peak. Those individual peaks that you're seeing in that green space are the atoms. Each of those little bumps is an atom. And this is actually a molecule of DNA. And you may be familiar with the shape of DNA. It's a double helix. And so you can kind of make out that double helix shape in the DNA atoms that we see in that green mountain right there. That's a picture of a molecule that we can actually get by using this special instrument called a scanning tunneling microscope. And so we have verified to a large degree that this idea of atoms is correct, to the extent that we can even produce a technology that allows us to look at them now, and we can look at individual atoms like this. It's pretty incredible. Okay, so at the most basic level, we have 3 states of matter: solid, liquid, and gas. A solid is when the particles have squeezed together as close as they can, and they're kind of locked in place, and they don't really move around anymore. They're stuck. They all get stuck. They've really stopped moving in a solid. In a liquid, they're pretty close together. They can usually get closer together, and they haven't stopped moving yet. So they still move around in a liquid, even though they're really close together. So a liquid and a solid, we can say that those types of matter are condensed matter. Condensed matter is when the particles are pretty much as close together as they can get. You can see that there is a little bit of space in between the liquid molecules. There's also a little bit of space in between the solid particles. So that's to say that liquids and solids don't have very much space in between them, almost nothing. So we call them condensed. They're very squeezed together. That's different than a gas. In a gas, the particles are not condensed. There's a lot of space in between the particles because they can kind of zoom away from each other. In a liquid, they're all stuck together. If we have a glass of water on the table, the water will evaporate eventually, but that takes a really long time. If we have a boiling pot of water on the stove, the water will disappear much quicker because the gas, as it boils and turns into a gas, the gas is free to float away because those particles aren't stuck together anymore. So in a solid, the particles are really close and they don't move. In a liquid, the particles are really close and they do move. And in a gas, the particles are not really close and they move really fast. You can see them kind of zooming around in that picture of the gas. They zoom around really quickly. So again, in a solid matter, atoms pack close to each other in fixed locations. That just means that they can't move. Neighboring atoms or molecules in a solid may vibrate or oscillate, but they do not move around each other. So even though they are essentially frozen in place, they still do wiggle around a little bit. They vibrate a little bit, and that's a function of temperature. When it's really cold, they don't vibrate much at all. As it warms up, they vibrate more and more and more. Solids have fixed volume and rigid shape. Ice, diamond, quartz, and aluminum are examples of solid matter. There are different types of solids. So a crystalline solid is one in which the atoms or molecules occupy specific positions to create a well-ordered three-dimensional structure. So you can see that shape on the right, the crystalline solid. We kind of have a sheet of red atoms, and then on top of that, a little bit to the left is another sheet, and then on top of that, a little bit to the right is another sheet, and on top of that, to the left is another sheet, and they kind of have this regular pattern, this repeating pattern that's the same from place to place. It just keeps repeating over and over again. That's a crystalline solid. It's well ordered. An amorphous solid, it's still, the atoms are really close together and they don't move, so it's still a solid, but they don't really have a repeating pattern. So you can see the amorphous solid, they're all just kind of squished together in some kind of random assemblage. And so examples of crystalline solids are like salt and diamonds. You can see a diamond has a very specific shape. But amorphous solids are things like glass, rubber, and plastic. And maybe you've heard that glass is actually, old glass can flow. And so if you, in some old buildings where the windows are hundreds of years old, if you look at how thick the glass is on the bottom, it's a little bit thicker than it is on the top, even though when that glass was made hundreds of years ago, the top and bottom had the same thickness. So that's showing you that the glass is actually moving. Those particles actually do move very slowly, even in glass, and they start to move because of gravity, and they kind of pile up on the bottom, and the bottom of the window becomes a little bit thicker. So amorphous solids, the particles don't fit together very well. They don't fit together as well as they do in a crystalline solid. And so in an amorphous solid, that allows them to bend or deform like glass or rubber. Rubber can kind of twist and bend. That's because it's amorphous and those particles don't make a very strict repeating pattern. And that kind of randomness of the particles allows them to kind of move around a little bit. There's a little bit more flexibility. So here's an example of a crystalline solid. You can see that the atoms are so well ordered that they order themselves over and over and over again in a cubic shape that we can actually see that cubic shape with our own eyes as the particles repeat that pattern over and over and over again. These crystals that form these cubes, they form cubes naturally, and they form a cubic shape like this. You could pick it up off the ground. They form a cubic shape like this because the atoms themselves are arranged in a cubic shape over and over and over again, a trillion times, until it gets so big that you can see it with your own eyes without using a microscope. So crystalline structures are very well ordered, very repeating patterns that repeat over and over and over again. Liquids are different than solids in that they have more space in between them usually. They're usually less dense than solids, and they also, the particles can move. So in a solid, the particles don't move. So if I have a rock that's shaped like a cube today, it's also going to be shaped like a cube tomorrow because the particles aren't moving and they're in a cubic arrangement. But if I have a liquid that I pour into a cup that's shaped like a cube, then that liquid looks like a cube. And if I take the same liquid and pour it into a cup that's shaped like a bowl, then the liquid looks like a bowl. So liquids can take the shape of the container they're in, and the reason they can do that is because the particles inside the liquid are moving. The particles inside a solid are not moving. So in a liquid, they can kind of rearrange themselves to take up the shape of whatever vessel they're in because the particles are still moving around. So liquids have a fixed volume because their atoms or molecules are in close contact. So again, even though there is a little bit of space in between liquids, there's not very much. So they're still pretty squished together, just like solids. Liquids are much more like solids than they are like gases. Liquids assume the shape of their containers because the atoms or molecules are free to move relative to one another. Water, gasoline, alcohol, and mercury are all examples of liquid matter. And finally, gas. Gases are different than liquids and solids in that the particles are pretty far apart from each other. They're not stuck together, and they can expand to fill the volume of a room. If I have a cup of water in a room that's 10 feet by 10 feet, the water is pretty much staying inside that cup. But if I bring a gas into a room that's 10 feet by 10 feet, the gas is going to spread out into that entire space. It will expand until it fills the void of the space that it's in. So that's much different. Gas is much different in that respect than liquids and solids. In gas, atoms or molecules are separated by large distances and are free to move relative to each other, and they move pretty quickly. You can see they've got these little tracers behind them in this image. That's to indicate that they're moving pretty quickly. Gases always assume the shape and volume of their containers. Oxygen, helium, and carbon dioxide are examples of gases. So because there is space in between the particles of a gas, I can squeeze a gas closer together and put the particles closer together. And you can actually do this experiment for yourself. If you take a syringe that doesn't have a needle on the end, it's just kind of an open port, and you put your finger on the port to clog it, like maybe one that you would use to administer medication to a child or something, and then you try to push the plunger down with your thumb on the other end, you can squeeze that gas a little bit. Maybe when you put your finger on the top, it starts at 10 mils, and then you squeeze it as hard as you can with your fingers, and you can squeeze it down to 7 or 8 mils, right? You can squeeze that gas with your own hand. You can make it take up less space. You can't do that with liquids or solids. If you put 5 milliliters of a liquid into that syringe, and you try to squeeze it with your fingers, you're not going to be able to squeeze it down to 4 milliliters. Same with a solid. It's not compressible. But gases, because there is that space in between the particles, you can squeeze the particles closer together. In fact, if you squeeze the particles closer together, they will start to turn into a liquid at some point. If we take a gas and we squeeze it together really tight, then we can turn that gas into a liquid because we can make the particles get close enough together that they start to stick to each other again, just like they do in a liquid. So this is just a table that kind of summarizes everything we just said about these different phases of matter or states of matter. Solids are pretty much stuck in place, but they can vibrate a little bit. They're really close together. They have a definite shape and volume, and they are incompressible. A liquid, they are free to move around each other, but they can't really break free. They're still stuck together. So their atomic spacing is close together. They have an indefinite shape because they'll take whatever shape of the vessel that they're in because they are free to move, but they still have a definite volume, and they are incompressible, just like solids. Gases are free to move relative to one another. So that means that they're not stuck together anymore. They can break apart from each other, and they kind of like pool. If you're playing a game of pool, the billiard balls, they kind of bounce off of each other when you strike them. That's kind of what gas particles do. They kind of run into each other, and then they bounce off of each other and then go a different way. So they're far apart. They have an indefinite shape and volume, and they are slightly compressible. We can squeeze them together. Okay, so now we want to make a distinction between pure substances and mixtures. So a pure substance is composed of only one type of atom or molecule. So atoms and molecules are different. So there are two different kinds of pure substances right off the bat. We can say something is pure if it has only one type of atom, but it can also be pure if it has only one type of molecule, even if that molecule has more than one type of atom. So we're getting fuzzy already in this distinction. So just bear with me. We'll clarify this as we move on. And a mixture is composed of two or more different types of atoms or molecules combined in various proportions. So a pure substance has only one type of particle, and a mixture has two or more types of particles. So we have to distinguish what a particle is. There's different kinds of particles. We have atoms as particles, which only have one color, right? Aluminum, they're all gray. Those are all the same atom. Or a molecule. A molecule is like H2O, and it has two different kinds of elements. It has an O and an H. It has a red sphere and a gray sphere. So if I have a cup of only H2O molecules, I can still say it's pure, but it has more than one type of atom. It has H and O. So pure substances can either have one type of atom or one type of molecule. A mixture has two or more different types of atoms or molecules. So here's what I mean by two different kinds of pure materials. Helium is an element. If you look on the periodic table, helium is element number 2. And so if I see a substance on the periodic table, its name is on the periodic table, I know it's pure. Aluminum, that's pure because its name is on the periodic table. Helium, that's pure. Its name is on the periodic table. Gold is pure. Its name is on the periodic table. Those are pure things. They're all, every substance that's on the periodic table is a pure substance when it's all by itself, and we call it a pure element. That's the periodic table of elements, right? So each of those substances, when it's all by itself, is pure, and it's a pure element. Pure hydrogen, pure helium, pure gold, pure oxygen, pure carbon. But we can also have another kind of pure substance. Water, for example, is not on the periodic table. There's no space on the periodic table that's called water, because we know that water isn't just one letter or one chemical symbol like H. Water has two chemical symbols, H and O. That means that water is made of two elements, hydrogen and oxygen, H2O. So water does not have its own space on the periodic table. So water is not an element. Water is made of two elements, hydrogen and oxygen. But water is still pure. If I have a glass of just H2O molecules, the only thing that's in that glass is H2O molecules, then that is pure water. And so the distinction here is not how many elements there are. This is what gets confusing for students. They go, oh, if it has one element, it's pure. If it has more than one element, it's a mixture. that's not true. We can see here helium is pure with one element, water is pure with two elements, glucose is pure with three elements, caffeine is pure with four elements. So you can have more than one element in a pure substance. The distinction is not how many elements you have. The distinction is how many different types of particles do you have? Look at the helium. What if we were to label each of those particles? I would say single gray dot, single gray dot, single gray dot, single gray dot, single gray dot. I would describe each and every one of those particles exactly the same. Each of those particles is a single gray dot. If I look at water, I would describe that particle as red dot with two gray dots, red dot with two gray dots, red dot with two gray dots, red dot with two gray dots. Every single particle that I see in that water picture is a red dot with two gray dots. So that means that every single particle in that picture is the same. They're all the same as each other. If there's only one type of particle, then it's pure. Even though water has more than one type of element, those elements gather up together into what we call a particle, in this case a molecule, and that molecule is pure because every single one of them, if I grab one of them, every single one meets the same description, red sphere with two gray spheres. So these are both different pure substances. When matter contains two types of atoms, it may be a pure substance or a mixture. A compound is a pure substance composed of different atoms that are chemically bonded in fixed definite proportions. A sample of water always has 2 parts hydrogen to 1 part oxygen. So every particle is always 1 red sphere, 2 gray sphere. And so we would call that a pure compound. A mixture, on the other hand, is composed of different substances that are not chemically united but are simply mixed together. So let's look at that. Air and seawater are examples of mixtures. So let's just look at the air all by itself first. Air, anywhere you are on Earth, if you're breathing air, that air must have oxygen in it because we need oxygen or else we would die. So if you're breathing air, it has some oxygen in it. But it's not pure oxygen. The air that we breathe is not 100% oxygen. There's other things in it. The air that we breathe, for example, has water vapor, right? You know, the humidity, depending on where you live, the humidity can be high or the humidity can be low. The humidity is a measure of how much water vapor, how much H2O gas is in the air. So it's not pure oxygen. It has oxygen. It has water vapor. It also has a lot of nitrogen. In fact, most of the air that we breathe is nitrogen, not oxygen. It's N2. The oxygen that we breathe is O2. The water that's in the air is H2O. The nitrogen is N2. Again, there's also carbon dioxide in the air. Maybe you've heard of climate change and global warming. Well, the problem is that there's too much carbon dioxide in the air that we breathe. Carbon dioxide comes from the tailpipe of your car when you burn gasoline or when you light firewood on fire, and the smoke that comes out has carbon dioxide. So that's another component of the air we breathe. So the air we breathe is a mixture. It doesn't have one type of particle. It has a type of particle that's called O2. It has a type of particle that's called H2O. It has a type of particle that's called N2, a type of particle that's called CO2, and many others. So there are lots of different things in the air we breathe, and they're all mixed together. So we call that a mixture. Same with the ocean. If I have a glass of pure water that has only H2O in it, I came from a purified water filter and it only has 100% H2O, then I can say that that H2O is a pure compound. But if I take a cup of seawater is not pure. Seawater, for example, you know it's salty. It's salt water. So if nothing else, I know that there's water and salt. Water and salt is a mixture. Salt all by itself is pure. Water all by itself is pure. If I mix salt and water together, I get salt water. That's a mixture. And so a mixture just has more than one thing all mixed together. There are 2 different kinds of mixtures. there's what we call a homogeneous mixture and a heterogeneous mixture. So in order to tell the difference between these two types, we should look at the prefix homo versus hetero. So homo means the same, and hetero means different. So a homogeneous mixture means that all of the components of the mixture are mixed up the same. A heterogeneous mixture means that the components of the mixture are not mixed up the same. They're not uniformly distributed. They're not all placed in equally distant from each other. So some components of the mixture might be closer together than others. If we have a homogeneous mixture, all of the components are exactly the same distance from all the other components. They're perfectly mixed up. So let's look at some examples. This is kind of a summary of how we can classify matter. So matter is stuff you can touch, okay? There are different kinds of matter. We can have pure substances or mixtures. Pure substances get broken down into two types, elements or compounds. An element has only one type of atom, and you can tell that something is a pure element if you can see the name of that thing on the periodic table. All of the pure elements, there's only 118 things that we can call a pure element, because there's only 118 elements on the periodic table. So if I ask you to classify an object, if you can see that object's name on the periodic table, then it is a pure element. If I ask you a bar of gold, gold is on the periodic table, that's pure. If I ask you a bar of silver, silver is also on the periodic table, that is pure. If I ask you a bar of steel, steel is not on the periodic table. If you look at all the names of all the things on the periodic table, steel is not one of them. Gold is a metal. Silver is a metal. Steel is a metal. Gold and silver are pure because their names are on the periodic table. Steel is not pure. Its name is not on the periodic table. Steel is a mixture. It's made of iron and carbon. Iron and carbon are on the periodic table. Iron is a pure element. Carbon is a pure element. If I mix iron and carbon together, I get steel. Steel is a mixture. It's not a pure element because it's made of two things that are mixed together. So, elements, their name is always on the periodic table. A compound can also be pure as long as there's only one type of particle. Every particle inside that substance is the same thing. If I have a sugar cube, then every single particle in that sugar cube is sugar, and sugar is a compound that's made up of these red ones and black ones and gray ones that we can see when we zoom in. Every single particle of sugar looks exactly the same, so we can say that's a pure compound. But if I took this sugar cube, and maybe it was Christmas, and I wanted red and green sugar cubes, and I took these sugar cubes and I used food coloring, and I dyed some of them red and I dyed some of them green, and I had red and green sugar cubes, now they're not pure anymore because there's red food dye and sugar. There are two different types of particles, green food dye and sugar, two different types of particles that are mixed together. Mixtures are when I have different things mixed together. So we can see here a cup of tea has water and sugar and caffeine. That one that has the blue spheres, that's caffeine. And so if in that cup of tea there are lots of things. So let's think about when we make a cup of tea. I have water, pure water that comes from a purified water filter. It's 100% pure H2O, and I boil it. When I have pure H2O before I've done anything to it, that's a pure compound. I have these sugar cubes over here. They're pure sugar cubes. I haven't put them in the tea yet. That's a pure compound. Sugar, it has a chemical formula just like H2O. Sugar is C11H22O11. And so sugar is just like water. They both have a chemical formula and they're pure compounds. Once I have this boiling water and I put the tea in it, then the tea starts to dissolve into the water, or be extracted into the water. And so now it's not pure water anymore. Now it has water and tea. And inside that tea, there's things like caffeine, and there's something that makes it brown, and there's other components of the tea as well that give it flavor. And so now I've created a mixture. I put a sugar cube in there and mix it up. Now it has another compound, sugar. It's all mixed up. A cup of tea that has water and tea and caffeine and sugar is a mixture, and we would call it a homogeneous mixture because all of the components are mixed up evenly. Every molecule of sugar is the same distance from every other molecule of sugar, and it's the same distance from every other molecule of caffeine. They're all equally spaced. They're all perfectly mixed up and perfectly far apart. I don't have two caffeine molecules next to each other in the whole mixture. They're all perfectly separated. If we look at a heterogeneous mixture, this is like oil and water. In a heterogeneous mixture, you can see the different components. There's the water on the bottom and the oil on the top. They're totally separated. In a homogeneous mixture, you cannot see the different components. The tea and the sugar and the water are all mixed together so closely that there's no way you could see the difference in those substances. It looks like one thing. A homogeneous mixture looks like one thing. A heterogeneous mixture looks like two things or more because they're not mixed up evenly. Whereas in a homogeneous mixture, I can say every sugar molecule is the same space away from every other sugar molecule, and it's the same space away from every other caffeine molecule. I can't say that about the mixture of oil and water. In the mixture of oil and water, all the oil particles are really close together, and all the water particles are really close to each other, but the oil and the water are all separated from each other. They're all really far apart. They're not equally spaced. They're not the same. So remember, homo means the same, and hetero means different. So homogeneous, they're all the same distance apart. Heterogeneous, they're not the same distance apart. All right, let's move to another classification. We can classify different kinds of changes. And so when we have an ice cube, we can melt it into water, we can boil it into steam, and it changes. We can see it go from a solid to a liquid to a gas. It's changing. And there are different kinds of changes. In this case, when an ice cube melts to a liquid and a liquid boils to a gas, we call that a physical change. Because before the ice cube melts, it's 100% pure H2O. After the ice cube melts, it's 100% pure H2O. It's just now it's a liquid instead of a solid. After the water boils, it's 100% H2O. It's just now a gas instead of a liquid. We can see in this picture, we've got liquid H2O in the coffee pot, all close together, and then gaseous H2O at the top of the pot as it boils away, where the molecules are further apart. But they're still the same. It's H2O as a liquid, it's H2O as a gas, it's H2O as a solid. The H2O doesn't change. It's always water, 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 water. If the substance is the same substance, the same molecule before a change and after a change, then we can say that that's a physical change. It's not a chemical change. So, boiling is a physical change. The boiling point of water is a physical property. When water boils, it turns into a gas, but the water molecules are the same in both the liquid water and the gaseous steam. It's H2O before and after the change. Another important point is that a physical change is reversible. I can turn an ice cube to liquid water to gaseous steam, and then I can capture the steam and cool it down and turn it into liquid water, and collect that liquid water and cool it down and turn it into an ice cube. The entire change is perfectly reversible. A chemical change is different. A chemical property, for example, is the susceptibility of iron to rusting. Rusting is a chemical change. When iron rusts, it turns from iron to iron oxide. So here we can see that before the rusting happens, we have iron. where's a pure element. All of the elements are the same. All the atoms are the same color. They're all gray spheres. After the change happens, we have gray spheres, and in between all the gray spheres are now red spheres. Those oxygen atoms infiltrated this iron matrix, and now we have oxygen atoms in between all of the iron atoms. This is different than what we saw in the previous slide. In the previous slide, it was H2O when it was water, and then it was H2O when it was gas. The particles looked exactly the same before and after the change. Here, before the change, there's only one element, but after the change, there's two elements. That shows that there has been a change here that we would classify as a chemical change in this case. This is irreversible. Once those oxygen atoms are added to the iron, there's no easy way to remove them. So we can melt an ice cube into liquid, and then we can freeze that liquid back into an ice cube. That's an easily reversible change. I can take an iron nail and leave it out in the rain and it will rust. There's no easy way for me to turn a rusty nail back into pure iron. That is an irreversible change. The chemical is different. It started as iron, and now it's iron 3 oxide. The chemical has turned into a different chemical. Rust is not the same thing as iron. It's changed. So we call that a chemical change. That's an irreversible change. Vaporization is another physical change. If we push the button on a lighter without turning the flint, then we have butane down below, which is this gas that's been compressed. It's under pressure, and so we've squeezed those gas particles so tight that we've turned them back into a liquid. So liquid butane is really just gaseous butane under immense amounts of pressure, so it's turned it back into a liquid. We forced those particles to squeeze them together back into a liquid. But when I push the button that lets the gas out, then I release that pressure, and when the liquid butane comes out into the lower pressure environment of the atmosphere, it turns back into a gas. So we go from a liquid to a gas. That's a physical change. Liquid butane, push the button, gaseous butane comes out. Physical change. If I captured that gaseous butane coming out of the lighter, I could squeeze it back down and turn it back into liquid and put it back into the lighter. So the liquid butane vaporizes to gaseous butane. The liquid butane and the gaseous butane are both composed of butane, so this is a physical change. The molecule is the same before and after, and it's reversible. In a physical change, bonds are not broken. Physical changes are reversible. However, if I push the button and I turn the flint at the same time to make a spark, then I have created a chemical change. So I push the button, which releases the gaseous butane, but lighting the spark gives that gaseous butane the energy that it needs to begin to react with oxygen that's in the environment, oxygen that's in the atmosphere. So if we push the button and turn the flint to create a spark, we produce a flame. We have liquid butane below, but once it reacts with oxygen, it's no longer butane. Now it's turned into carbon dioxide and water. And that chemical change also produces energy. And we can see that energy as light, and we can feel that energy as heat. So the chemical change is associated with releasing light and releasing heat. The butane molecules react with oxygen in the air to form new molecules, carbon dioxide and water. In a chemical change, bonds are broken, and a chemical change is irreversible. Just like I can turn a nail to rust, but I can't unrust a nail, I can turn butane, I can burn it and turn it to water and carbon dioxide. I can't easily take water and carbon dioxide and turn them back into butane. So we say that's an irreversible change.